Welcome back to Calculus 2. So today we are going to prove the fundamental theorem of calculus. The fundamental theorem of calculus is the reason why we don't have to try to do limits of Riemann sums by hand. And thank goodness for that, because nobody wants to do limits of Riemann sums by hand if you can possibly avoid it. Now that's not to say that Riemann sums are not important, and I'm going to just quickly tell you why we still care about Riemann sums. The reason is because we're going to see throughout this semester, there are a lot of applications where we'll come up with a problem. And it won't necessarily be obvious how to solve the problem exactly, but it will be obvious how to approximate the problem, and it will also be reasonably obvious that if you take the limit of these approximations, you get the exact answer. And what we'll see is that these approximations that we get, well, they will end up being able to be interpreted as Riemann sums. And because we can interpret them as Riemann sums and we're taking the limit, we can then say, that is actually a problem that we can solve using the fundamental theorem of calculus. So it is important to understand Riemann sums, even though our goal is to get away from Riemann sums as fast as we possibly can. It's just, we're still going to encounter Riemann sums. We're going to translate them into something that is not Riemann sums. But in order to do that, we do need this fundamental theorem of calculus stuff. Now, the interesting thing about the fundamental theorem of calculus is that it predates Riemann sums. It predates Riemann's work. In fact, you can prove the fundamental theorem of calculus using just a few properties of definite integrals, okay? And that is why Newton was able to prove the fundamental theorem of calculus, even though he didn't really have any, he didn't really do Riemann sums exactly. So I'm going to show you the properties that we need for the definite integral to do the fundamental theorem. Then we're going to prove the fundamental theorem. Once we've got the fundamental theorem proved, let me put it this way. When we see these properties, it's going to become clear from what we said last time that the Riemann integral, the limit of the Riemann sums, definitely has these properties, and therefore the fundamental theorem applies to the Riemann integral. But in fact, the fundamental theorem applies not just to the Riemann integral, it applies to anything with these properties. And the reason that's important is because the Riemann integral is not the only one that you can define. You can also define some other types of integrals called the Lebesgue integral and some other types that are in some ways better than the Riemann integral, but they also are a lot more technically complicated. So usually in this class, we're going to be working with the Riemann integral, but the fundamental theorem applies to all of these. So what are the properties that we want to have here? Well, essentially, the basic properties that we're going to want to have are the ones that we said last time. So the integral from a up to b of a times f of x plus b times, why did I do a and b? We need other letters here. Let's say k and l, so these are just constants, dx. This needs to be equal to the integral from a to b of f of x dx multiplied by k plus L times the integral from a up to b of g of x dx. By the way, this property that you can split the integral over addition and that you can take constants out of the integral, this means that integration is what is called a linear functional. Don't worry too much about what that means. Just later on, if you ever encounter this term, this is what they're talking about, something like an integral. It's known as a linear functional. A functional just is something that takes a function and assigns a number. The linear part is that it splits over addition and you can pull out constants. So that's one property. And this is definitely true of the Riemann integral. The other properties that we're going to need are also things that we know are true of the Riemann integral. So the integral from a up to b of some constant times dx should be that constant times b minus a. We verified that that was true last time. And then we need one more property, which I don't actually think I mentioned in my last video, but it's not hard to see that this is true for the Riemann integral. if f of x is bigger than or equal to g of x on some interval from a to b, then we need that the integral from a up to b of f of x dx is bigger than or equal to the integral from a up to b of g of x dx, if, of course, both of these things are defined, because maybe we can't actually define these integrals, but provided that they are defined, we need to have this inequality hold. Well, it's not too difficult to see that this is true for the Riemann integral, and I don't want to go through all of the details here. I don't think they're that enlightening, and they're in your book if you really want to check them out. But basically, write down a Riemann sum for the f of x's. You will always find for any given number of rectangles, there will always be a Riemann sum for f that is bigger than or equal to the Riemann sum for g. And therefore, since one of the Riemann sums for f is always bigger than or equal to one of the Riemann sums for g, the sandwich theorem tells us that in the limit of the Riemann sums for f has to be bigger than or equal to the limit of the Riemann sums for g. So again, it's not like, it's one of these weird things in math where it's not necessarily hard in the sense of being a very deep, complicated result, but it's kind of an annoying technical thing to just write down all of the limits and say, and now the sandwich theorem. There's kind of a lot of things in mathematics, and my feeling is that we'll see enough of that this semester that I don't want to spend a lot of time talking about it right now. So we're going to just say, yes, this is true for the Riemann sums, and we're going to use it. I believe everything else we covered last time. So the one other thing that we're going to want to use is the fact that the integral from a up to b of f of x dx is equal to the integral from a up to c of f of x dx plus the integral from c to b f of x dx. And we talked about how that is true for the Riemann integral last time. Now, putting all of these things together, we're going to show that any integral that has these basic properties that we just talked about is going to obey the fundamental theorem. And here's the thing. If you want your integral to express something like, why am I drawing an integral symbol? I'm trying to draw a graph. If I want my integral to express something like this area, this area, this area, a1, a2, and a3, if I want my integral from a up to b of f of x dx to be interpreted as a1 minus a2 plus a3, it really has to have those properties that we just talked about. If the integral is going to be something that has to do with areas, and it counts these areas positively and areas below the axis negatively, it's got to have those four properties. And that's kind of what the early calculus people knew about integrals. They knew this is what we want our integral to symbolize or to give us, and therefore it has to have those properties, because that's how areas will behave. It reflects the fact that, for example, if one area is contained within another area, it should be a smaller area. It expresses the fact that if I break up an area into pieces and I add the areas of each piece, I should get the total area. Things like that are really what those four properties are expressing. One of the properties, the one about integrating constants, expresses the fact that rectangles should have an area that is width times height. Okay, so they were able to say the integral, if the integral is to be interpreted in this fashion as telling us something about areas, it has to have those properties. And that's why they were able to prove the fundamental theorem of calculus, even though they didn't have Riemann's definition of the definite integral. Now, what does the fundamental theorem of calculus tell us? Well, let's suppose f is continuous on the interval from a up to b and x is some point that is in the open interval from a to b. So it's not equal to a and it's not equal to b, but it is somewhere in between the two. Then what we can say is the derivative of the integral from a up to x of f of t dt is equal to f evaluated at x. This is one form of the fundamental theorem of calculus. There is a second form that follows fairly straightforwardly from this first form, but this is the form that's easier to prove, so that's why we do this one first, or at least that's why I do this one first when I do it. Some people might like doing it the other way. I find this to be the more straightforward way to think through it, and then we're going to figure out the other direction in a minute. So how are we going to do this? Well, the way that we're going to do this is we're going to write out this derivative. So the derivative of the integral from a up to x, f of t dt, this is going to be equal to the limit as h goes to 0 of the integral from a up to x plus h, f of t dt, minus the integral from a up to x of f of t dt, all divided by h. That is the definition of the derivative, just applied to this wonky looking function. So what can we say next? Well, this is going to be equal to, then, I'm going to split up this integral into two pieces. So this is the limit as h goes to 0 of the integral from a up to x, f of t dt, plus the integral from x up to h, f of t dt, and then we still have minus the integral from a up to x, f of t dt, all divided by h. Now, we said last time that continuous functions are integrable, and therefore everything involved here is well defined, at least for the Riemann integral. Now, this is where kind of the early calculus people, they were a little bit sloppy on this because they couldn't prove that these integrals should exist. What Riemann was able to do was he was able to give a definition of the integral that made it very clear that these really do exist, okay? And so from a mathematical perspective, we like to be what's called rigorous, logically rigorous. In other words, we don't want to say, we hope these exist, and if they do, this works out. We want to be able to say, yeah, we can prove these exist using logic. That's what Riemann did. He was able to give a definition where we can prove that these things exist. Before him, you could prove the fundamental theorem, but you kind of had to make this assumption that the integral was well defined. So, assuming this is well defined, that means that I can cancel these two things, and therefore, I get, writing this on the top, I get the limit as h goes to 0 of 1 over h times the integral from x to x plus h, f of t dt. Now here is where I'm going to make the following claim. Going to erase this part down here. If you need to refer back to it, feel free to rewind for a bit, but we're going to erase that because I need some space here. What I want to claim is this. On x up to x plus h, or x plus h to x, depending upon whether h is positive or negative, when h is less than the absolute value of, actually, how do I want to put this? H is less than the minimum of the absolute value of x minus a and the absolute value of x minus b. f is continuous, because it's actually continuous from a to b entirely. So the point is that if I have, here's my a, here's my b, here is my x, as long as x to x plus h is reasonably small, f is going to be continuous on this interval. And because it is continuous, the extreme value theorem there is capital M of h, the maximum on this interval, and there is little m of h, the minimum on this interval. Why is this true? Well, it's because on a closed interval, a continuous function always achieves a maximum and a minimum. And what that means is that I can say, on this interval, the integral from x to x plus h, f of t dt, if we assume here that h is bigger than 0, if h is less than 0, the same argument is going to apply, but it's going to, all the signs are going to be flipped around. We're going to have that h times little m of h is less than or equal to this integral less than or equal to h times capital M of h. Actually, this is also assuming that f of x is positive here. Let me just throw that in there. Again, if the signs change, you still get this kind of sandwiching effect. It's just that they might flip the direction of the inequalities. But otherwise, everything is fine. And in terms of graphically, it's kind of easy to see what's going on here. What we are saying is that from x to x plus h, if I have some function here, the area of this region has to be sandwiched between the area of this smaller rectangle and the area of this larger rectangle. So that's really what this is saying. Like, there's a very, it's complicated and annoying to write this out, but in terms of the geometry going on, I think it's actually reasonably nice. Like, it's just this little picture, okay? Now, what can we do with that? Make sure that you understand this, because unfortunately, again, I'm going to have to erase this because we're working with a tiny whiteboard. So what we can say is, because of this sandwiching, if I multiply everything here by 1 over h, the h's cancel, except for the one in the middle, and that's what I've got here. So then what we have is that little m of h is less than or equal to 1 over h integral from x up to x plus h, f of t dt, less than or equal to capital M of h. And by the sandwich theorem, this is true in the limit as h goes to 0 as well. Of course, technically, we're only doing the limit from the right at this point, but the same kind of argument applies to the limit from the left. Okay, now, we're kind of done with all the tricky stuff, because at this point, what we can say is, because f is continuous, as h goes to 0, little m of h and big M of h both approach f of x. Because if you think about it, as I make the interval smaller and smaller, the maximum and the minimum of the function are going to have to approach the value of the function at the left endpoint of that interval. And then if h is negative, they have to approach the value at the right endpoint. The sandwich direction becomes the opposite, but the same argument applies. And what this shows us is that this in the middle is sandwiched between f of x and f of x. So the only thing that this can be is f of x. And that establishes the fundamental theorem of calculus. To indicate that our proof is done, we can either put a square box, which is the way that I like to do it, or some people prefer to use QED, which is Latin for quod erat demonstrum. You'll have to excuse my terrible Latin pronunciation. It means that which was to be proved or demonstrated. But I like the little box. It's easier to make than QED. So this gives us the first form of the fundamental theorem of calculus. The other thing that this proves is this means the integral from a up to x of f of t dt is an antiderivative for little f of x. An antiderivative is a function, capital F of x, where the derivative of capital F of x is little f of x. So there is another way of thinking about this. This function has to be an antiderivative. And the other thing that we know about antiderivatives is that all antiderivatives are the same up to possibly shifting by a constant. But we know capital F of a here should be the integral from a up to a, f of t dt, and that should be 0 because the integral from a to a is always going to come out to be 0 no matter what. Go back and look at the Riemann sum. If a and b are actually the same number, then everything is getting multiplied by a 0, so we're just taking the limit of a bunch of zeros. Well, if that is the case, the integral from a up to x, f of t dt, is actually equal to capital F of x minus capital F of a for any antiderivative capital F, because this is an antiderivative. This whole expression is an antiderivative. Remember, this is just some constant. And this has the requisite property that it is equal to 0 when x is equal to a. This is another way of thinking about the fundamental theorem of calculus, and usually the way that we write out this result is the integral from a up to b of f of x dx is capital F of x evaluated from a to b, which is defined as f evaluated at b minus f evaluated at a, where f is an antiderivative for little f. And this allows us to compute definite integrals for any function that is continuous, and we can find the antiderivative. So now I do want to say this does depend upon f being continuous. So that's an important thing. You can't forget that. But as long as we can find an antiderivative, and as long as our function is continuous, we can now compute these definite integrals. And that is a vastly superior thing to trying to mess around with Riemann sums, okay? So this is why, again, Riemann sums are important to be able to technically say, yes, this exists, it makes sense, it's well defined. However, nobody wants to actually compute one directly by hand. And this is not, like, this is something you've seen before in Calculus 1. We define the derivative using this limit. However, nobody wants to compute a limit by hand if you can get away from it. So we work out some rules for how do you actually calculate the derivative. And these rules are much simpler than calculating limits by hand generally are. Well, similarly, we use the Riemann sum to prove that the integral is well defined, but we then say, okay, here's the rules for actually calculating what that comes out to be, and they're much simpler. They just involve calculating these antiderivatives. So that's the good news. Thus, you're probably expecting some bad news, and I'm going to tell you the bad news right away. The bad news is that antiderivatives can be really, really tricky to calculate. In fact, a bunch of what we're going to be doing this semester is figuring out how in the world do you find an antiderivative. But I can tell you right off the bat, finding an antiderivative is harder than finding a derivative. In fact, finding derivatives is the sort of thing that you can program a computer with an algorithm that will find the derivative of any given expression, okay? If it is a reasonable expression, like built out of algebraic functions and trig functions and exponentials and things like that. You build a function out of those things, you are guaranteed that the computer can find a derivative written in terms of those things as well. Not so much for the antiderivatives. Just because you have a function that can be written out in terms of algebraic operations and exponentials and trig functions and the like, does not mean that you can find an antiderivative for it. And that is one of the senses in which finding antiderivatives is automatically going to be harder. We don't necessarily we know that they exist as functions, but we don't necessarily know that you can express them in a nice way, in what we call a closed form expression, using algebraic operations and exponents and those types of things, trig functions, the basic stuff that you're familiar with working with in terms of functions, okay? So finding antiderivatives can be a tricky thing, and we're going to spend a lot of time working on how do you find them. But really, every rule for differentiation is going to translate into a rule for anti-differentiation. So some of the basic rules here are like, from the fact that the derivative of x to the n is n times x to the n minus 1, we can figure out that an antiderivative for x to the n is going to be x to the n plus 1 divided by n plus 1. Another thing that we can do for finding antiderivatives is we can say things like, well, we know what the derivative of e to the kx is, so the derivative of e to the kx is k e to the kx, and therefore if we start with the function e to the kx, the antiderivative is going to be e to the kx divided by k. So that's another antiderivative rule that you can use. And then we also have a bunch that we get from working with the trig function. So for example, the derivative of sine x is cosine x, so that tells me the antiderivative of cosine x is sine x. The derivative of cos x is negative sine x, so that tells me the antiderivative of sine x is negative cosine x. And then there's others for the other four trig functions. I will leave it to you to go back and refresh your memories on that kind of thing out of the textbook. But I do want to make sure that you really do go back and check that, because you do need to see, here's my, to remember those kinds of things for future reference. So I do want you to make sure to go back and check the other trig functions for that kind of thing. In fact, you should also check the derivatives of the inverse trig functions, because we are going to be using those in the future as well. So we'll refer back to that as we need them. For now, I'm just going to think about those. The other thing that we know about antiderivatives is that taking antiderivatives are linear. So if f and capital F and capital G are antiderivatives for little f and little g, then k times capital F of x plus L times capital G of x is an antiderivative for k times little f of x plus L times little g of x. This is not too difficult to verify. In fact, I'm going to encourage you, pause the video at this point, take a minute to convince yourself of this fact. The way you want to do this, take the derivative of this expression here and see that what you end up with is this expression here. Okay, so hopefully you were able to do that. If you got into too much trouble with it and weren't able to figure it out, let me know and I'll be happy to help you out with trying to figure that out. But hopefully you were able to convince yourself of this fact. So, since antiderivatives are linear, that allows us to compute antiderivatives fairly easily, and we can use those antiderivatives in order to solve problems involving definite integration. For instance, if I need to do the integral from 1 up to 3 of, let's say, 3x squared minus the sine of pi times x dx, well, what I can do here is I can say, all right, let's take a minute to figure out the antiderivative. That's going to be 3 times x cubed over 3, and the 3's will cancel. And then this is going to become plus 1 over pi times the cosine of pi x, because the derivative of cosine pi x would give me negative sine pi x multiplied by a factor of pi, and so that's where that comes from. And then I can evaluate this from 1 up to 3. So that's going to give me 3 cubed plus 1 over pi times the cosine of 3 pi minus 1 cubed plus 1 over pi times the cosine of pi. And that's going to give me 27. And then the cosine of 3 pi, that is going to be same as the cosine of pi. So these are actually going to cancel with each other. 27 minus 1, which comes out to be 26. And so using this technique, using the fundamental theorem and the antiderivatives, I can figure this out without having to mess around with Riemann sums. Now, to be perfectly frank, I don't know how you would directly go about the Riemann sums for this thing. I just really have no idea. There might be some clever way of doing it. I mean, there's usually clever ways of doing some of these things that people can come up with, but it would take me a really long time to figure out how to do this using Riemann sums. It would not be an easy task. Doing it with antiderivatives, kind of straightforward, okay? So here's what I would like you guys to do for the next few minutes. I would like you guys to take a look in your textbooks and do a little bit of practice here. I'm sorry, I'm trying to bring up your textbooks, which I really should have had going. And take a look here in chapter 5. Where is chapter 5? Having trouble finding chapter 5. That's chapter 7, which means we're way too far. That's chapter 6, which means we're way too far. There, chapter 5. So I'd like you to take a quick look in chapter 5 and refresh yourself with some of the basic antiderivative problems from sections 5.2 and their applications in 5.3. And hopefully you guys will be okay with dealing with those kinds of things. I would say particularly look at 5.3, and actually I guess 5.4 has some antiderivatives as well. Now, we've worked out just a few rules for antiderivatives here. What we're going to want to ultimately do is to work out even more rules for antiderivatives that we can use. And the first rule that we're going to want to cover, beyond sort of the basic, we know that this is the derivative of some simple function, those are kind of the easy rules, right? Like the derivative of x cubed is 3x squared, so the antiderivative of 3x squared is x cubed. That's kind of a fairly straightforward rule, but there are more complicated rules that we're going to need to deal with. The first complicated rule is going to be the substitution rule, and I think that's probably worth putting into a separate video. So I'm going to end this one here, and I will upload another video in a couple days for you guys. Talk to you later.